So the third strengthening mechanism is introduction of the precipitates. And an example of this particular strengthening mechanism would be the introduction of silicon carbide in iron or aluminum. And again, to explain why this mechanism works is as follows. So if you have a certain plane of atoms and the dislocations will glide, or they will move throughout the material, and if there is a precipitate that has different composition, and in this particular case, it's silicon carbide, it's a ceramic material. So last time you learned that the dislocation in ceramic materials do not propagate easily, right? So when the dislocation comes to this particular area, right? So the material is slipped here, but it's unslipped here. So when the dislocation reaches the point of the precipitate, it effectively has to slip the precipitate itself, right? So it has, the dislocation itself slips the two planes. So what that means is that from precipitate that is relatively uniform, it's a particle within the material, you have to slip this precipitate within the material itself. And again, this is silicon carbide, it's a ceramic material, it's very difficult to do that, right? So this would be in a cross-section, and what that physically means and how dislocations then do propagate, if you look from the top view, the dislocations will, instead of going in a straight line, the slipped part of the material will have different types of shapes, right? So it will be slipped here, but it will try to avoid the regions where the precipitates are. Again, very, very common type of the strengthening mechanism. And just one very, very famous example is the strengthening of aluminum using silicon carbide precipitates. So, so most of the airplanes nowadays, or they used to be, made of aluminum. Do you know why are planes made from aluminum? Why do we use aluminum? Yes. Light, cheap, and also it's relatively resistant to corrosion, right? It forms a very, very thin layer of oxide, but then it doesn't corrode anymore. So if you have really extreme environments or water and things like that, it's also very resistant. But it's it's lightweight material. However, you can deform it plastically very easily. So if you take a piece of aluminum foil or a material and you try to deform it, it's very easy to do so. So to change or to influence the mechanical properties of aluminum. So this would be the micrograph of aluminum that has been strengthened with silicon carbide precipitates. So the dark spots, or in this particular image, will be silicon carbide precipitates that are embedded in aluminum. So aluminum used to be, and it's still a major material used in production of airplanes. Nowadays, do you happen to know, for example, a Dreamliner? What is the material that is used for Dreamliner construction? It's a carbon-based or carbon fiber-enhanced polymer types of materials, right? Again, you're trying to develop materials that are relatively lightweight, that are resistant to environment, and that are relatively cheap, right? Aluminum used to be that.
Well, why did they change the material? How is it better?
So it's lighter. So, for example, the relatively large airplanes are made from this. So there is a certain calculation of how much does it cost for short distances, for long distances, and you make the calculation between the weight, between the cost, and how much do you save in fuel and things like that. And it turns out that nowadays these new composites are relatively inexpensive in comparison to other materials that used to be used for this. So again, we do need to know something about the strengthening of the mechanism. At the same time, we do learn about other materials that might substitute them. So finally, the fourth strengthening mechanism is so-called cold work. And again, the cold work, or so-called strain hardening, simply comes from deforming the material multiple times. And there are different ways how you can do this. You can forge, you can draw the material, you can roll it, and there are different ways. So you take a piece of material, you deform it multiple times, you go through this process many, many times. So I can ask you a question: why would this strengthen the material? What happens if you plastically deform the material? Why would this work, right? What that means is that I plastically deform material more and more times, and it becomes stronger and stronger. Why is that happening? Yes?
So if you deform it more, you're introducing more dislocations into the material, which makes it stronger because it allows it to hold more stress.
So you're right. So when you're plastically deforming the material, you're introducing more and more dislocations, right? And you mentioned that that allows you to hold more stress, and we have to understand why that's the case. But you're basically increasing the density of the dislocations, right? You start with a relatively modest density of the dislocations. You increase this by orders of magnitude. And just a typical image of a hard work material is given here. So again, these would be dislocations. So dark lines here indicate dislocations. So this is electron microscopy micrograph showing dislocations in a case of titanium after cold work. And you can see that somehow dislocations are entangled. What that means is that density reached such a level that the dislocations start to interact. So the question is, why would this interaction of the dislocations even matter, right? So we can understand this by, for example, looking at the local strains around the dislocations. So if you remember, we mentioned that there is the compression and around the dislocations, and if you have two dislocations with the same Burgers vector, when they come close to each other, when the density is so high, they will basically try to repel each other because of the local strains. And again, you can try to understand this more intuitively. If you have this dislocation here, and there are planes that are deformed around it, so there is another dislocation here. So for this first dislocation to propagate, again, ideally, the propagation will be relatively easy if the crystalline planes are perfect, right? But if you find another dislocation, what that means is that the strain around this dislocation somehow prevents the first dislocation to move. So an opposite case happens when you have dislocations with the opposite Burgers vectors. Then these local, and how that would look like is that, for example, you have dislocation that looks like this. Then you have another one that looks like this. And again, because they have opposite Burgers vectors, when they come close to each other, they will cancel each other, right? So again, there is some, ideally, by increasing the density of the dislocations, you have this particular situation when you have Burgers vectors of the same direction or the same type, and they will then prevent each other from moving throughout the material. And just to illustrate how much you can change the density of the dislocations, let's just look at one particular case. So typically the dislocation density is expressed as the total dislocation length over the unit volume. What that means is that if you want to calculate the dislocation density, you measure the length of the dislocations in a given piece of a material, and then you divide this by the volume of that material, right? So this material itself has a certain volume. We take a picture of this, we calculate the length of these dislocations, and we divide by volume. So this will be the density of the dislocations. And this will be, so this is the total dislocation length divided by the unit volume, or it is the number of the dislocations divided by an area. So the units are either in centimeters squared or millimeters squared. 1 over a millimeter squared. Yes?
Is there ever, can you know from, I know for our PSEB, we had a question with the dislocation density. I wasn't sure if what they were giving me was total dislocation length or number of dislocations per area. Is there a way that, is there like a difference between the two, or can you just assume one or the other?
I'm not sure that I understand the question, but typically you have to match the units, right? So if it's the number of dislocations, then it's per area. If it's the length, then it's per unit volume, right? But at the end, the units will be 1 over a millimeter squared, right? So, so if you, for example, have a carefully grown single crystalline materials, the density of dislocations will be 10 to the third, or 1,000 per millimeter squared. So what that means is that even when you very carefully grow a material, there will be a certain number of dislocations that are produced simply through the growth process. So it's very often, it's something that you cannot eliminate totally. Then if you deform this material, you can increase the density to really significant numbers, up to 10 to the 9th, 10 to the 10th of dislocations per millimeter squared. So this is 6 to 7 orders of magnitude simply by cold working material. And then, so this will just tell you why this material is stronger than the carefully grown single crystalline material. And then there is an indication here that you can reverse this process. So I said here, Well, if you heat treat this will reduce the dislocation density. What that means is that even if you hard work the material, by annealing the material, you can reduce this density even further, and we'll talk about this in a second. But again, you can then reduce this to the values of 10 to the 5th up to the 10 to the 6th per millimeter squared. So the reason why I'm mentioning these numbers is just to give you a feeling about typical orders of magnitude, and also to tell you that you can indeed influence these densities. So even if you have a starting material with a certain density, if you want to increase it, you can cold work it. If you want to reduce the density, you can, for example, try to anneal the material. Okay? And the annealing reduces the density of the dislocations because of the following fact. So if you have, for example, 2 dislocations, and if you anneal the process, what happens when you increase the temperature of the material? What happens with the atoms within the material? Whether they're intrinsic atoms or impurities. They have more energy, that's right. And as a consequence, what will happen? Yes? They can move, they can start to diffuse, right? So what this first picture is simply means that there is a point in the crystal where you have 2 dislocations, in this particular case of the opposing Berger's vectors, and there is one piece that is missing atoms. And if you increase the temperature, the atoms within the material can diffuse, and they will basically occupy this region that was initially unoccupied. And this, as a consequence, these 2 dislocations will move down, and one will move down, one will move up, and they will cancel each other. Again, so this is just to let you know that the diffusion mechanism that we mentioned before is again very, very relevant when we talk about dislocations. So all of these processes are interrelated. Okay? So with this, we are finishing the discussion about dislocations. And as a summary, I give you a list of things, and we won't go through this, but I would strongly encourage you to try to think about this, and either on Friday or on Monday, we will go again through this list. But the idea is that if you can fill out the gaps in this slide, then you know everything about dislocations. So if you can identify or define what the dislocation is, if you can explain why we introduced these dislocations, why they were postulated in 1931, how do we describe them, what are the descriptors, if you know what type of dislocations exist and what does it mean, what happens when you apply a stress onto the material, what is a slip system, and how do you define the strengthening mechanism, then in principle you know what you're talking about. So think about this, and I strongly encourage you to do so, and then we will come back to this slide again.